Chapter 2. Motion along a straight line. It covers position, displacement, velocity, and acceleration. Constant acceleration, free fall acceleration. You can find them in a timeline. Position, displacement, velocity, and acceleration. Motion. For the time being, we examine some general property of motion that is restricted in three ways. The motion is along a straight line only. That is one-dimensional. 2. The cause of a motion will not be specified until later. We study kinematics. 3. The moving object is either a particle, by which we mean a point-like object such as electron, or an object that moves like a particle, such that every portion moves in the same direction and at the same rate. Position and displacement. To locate an object means to find its position relative to some reference point, often the origin or 0 point of an axis, such as the x-axis in the figure. This is reference frame, okay? This is the origin of the frame. The position directions of the axis is in the direction of increasing number coordinates, which is towards the right as the figure is drawn. In this case, it's 1, 2, 3 is increasing direction. It's positive direction, okay? The opposite direction is the negative direction. This is the negative direction. A change from one position x1 to another position x2 is called a displacement delta x, where delta x equal to x2 minus x1, the final minus initial. The symbol delta, which represents a change in the quantity, means the final value of that quantity less the initial value. Displacement is an example of a vector quantity, which is a quantity that has both direction and a magnitude. Delta R equals R2 minus R1 equals R final minus R initial. Velocity and speed. Average velocity and average speed. The average velocity V average is the ratio of the displacement delta x that occurs during a particular time interval delta t to that time interval delta t. That is, look at this. The green line is the way a particle moves. Okay. The average velocity, v velocity, from 1 second to the 4 second. This is the 1 second. This is time to 4 second. This is position x. Okay, is v average equals delta x or delta t. When t equal to 1 second, and here, x1 is minus 4. When t equals 4 seconds, go to here, the x2 is 2. So we put them inside. 1 is minus 4, 4 is 2, we get 2 meters per second. The average velocity during 1 second to 4 seconds. Average speed, S average, is a different way to describe how fast a particle moves, whereas the average velocity involves the particle's displacement, delta x. The average speed involves the total distance covered, for example, the number of meters run, independent of direction for average speed. That is, average speed is total distance no direction over delta t. Average speed also differs from average velocity in that average speed does not include direction and thus lacks any algebraic sign, no plus minus, because no direction. Sample. A man standing at the orange of a reference frame walks 2 meters along the positive x direction in a second, and then walks along the negative x-axis 3 meters in the following second. Find the average velocity and the average speed in this 2-second interval. Now see, he started from orange. First second, he was towards the positive thing, 2 meters. And in the following second, it got negative direction, 3 meters. I call this R1 and I call this R2. Okay, so in R1 is 2I, where I is the unit vector along x-axis, is this direction. So R1 is 1, 2, 2I. R2 is 1, 2, 3, minus 3I. Then the R initial is 0 in 2 seconds. R final is R1 plus R2. So 2I minus 3I. So the R1 position is equal to minus I. This is minus I, that's here. Okay. So delta R equal to R final minus R initial. Minus I minus 0 is minus I. And delta S, we don't care the direction, is 2 plus 3 is 5. So in that case, we get V average is delta R over delta T. It is delta R here, minus R. T is 2 taken over 2, minus 0.5 I. And S is delta S over delta T. 5 over 2 is 2.5 meters per second. This is average speed. This is average velocity. Velocity has a direction. Average speed does not. Instantaneous velocity and speed. The instantaneous velocity, or simply velocity, v at any instant, is obtained from the average velocity by shrinking the time interval delta t closer and closer to 0. We can imagine that one. Okay. As t dwindles, the average velocity approaches a limiting value, which is the velocity at that instant. This is average velocity. When delta t approaches 0, we get instant velocity, instantaneous velocity. This looks familiar. From calculus, this is the definition, dx dt. So velocity is the derivative of displacement, or derivative of position with respect to time t. It can be larger than 0, equal to 0, or smaller than 0, depends on the situation. In the language of calculus, the instantaneous velocity is the rate at which a particle's position x is changing with time at a given instant. Let me repeat it. The instantaneous velocity, v, is the rate at which a particle's position x is changing with time t at a given instant. That's the definition of instantaneous velocity or velocity. Okay, well, look at this one. Okay, look at this one. Okay, this is the curve of position. All right, we want to find the velocity. What do you see now? According to the equation, the velocity of a particle at any instant is the slope of its position time curve at that point, representing that instant. For example, we want to find the velocity at time t equal to 3 seconds. And we're looking for the t times the second. At this point, the velocity by calculus is the tangent theta. Tangent theta. Remember that? Okay. We do a tangent line for this curve. And this is a theta with respect to positive direction of x. Okay. And tangent theta is dx dt. Okay. From calculus. So this v, at any instant, we do a tangent of this curve, and we find the theta, tangent theta is dx dt, is the velocity at that moment. At different point, we have different tangent. We have different tangent theta, so it's different. Okay. What is speed? Speed does not have direction. Speed is the magnitude of velocity v. The unit is, this is a distance, this is time, meter per second. So velocity equal to dx dt. Dx equal to v dt. We do the integration on both sides. This is integration, differentiation, cancel out. So we get xt equal to integration of vt dt integration. Okay, this is x, the position, plus constant from the calculus. This constant, it defines the initial condition. Okay. Constant is determined by the initial condition. For a same moment, the velocity of an object can be either positive or negative. Depends on how do you choose the direction of the reference axis. Okay, the same movement depends. For example, this is v, your direction. If we choose the positive direction of the refrain, it's this direction, so this is positive. The same movement, exactly the same physical movement. If we choose the reference of axis direction, positive is toward the left, and this one becomes a negative number. Okay, this depends on how you choose the reference frame, the positive direction. Sample. The position of a particle moving on the x-axis is given by xt equal to 7.8 times 9.2 t minus 2.1 t cubic. Question A. What is the velocity at t equal 3.5 seconds? Question B. Is the velocity constant or is it continuously changing? It's given x. Okay. We want to find, question A, velocity. The velocity is the dx dt. We do the derivative with respect to time t. This is 0. This is a 9.2. This is 3 times minus 2.1 t squared. So we get this equation. V is a function of time t. When time t changes, v changes. So at this moment, different moment, you have different v. So when t equal to 3.5 seconds, we put t equal to 3.5 in. And we get a velocity at this moment. It's minus 68 meters per second. That means the velocity is in the negative direction of the x-axis. Okay, acceleration. The average acceleration over an interval delta t is computed as t1, you have a velocity v1. After delta t, t2 equal to t1 plus delta t, you have velocity v2. Then delta v over delta t is average acceleration. And then usually we are interested in instantaneous acceleration or simply acceleration. A is the derivative of the velocity of this one. The instantaneous acceleration is the average velocity limit when delta t close to zero. And this is, we know, familiar. Okay? Why it's familiar? Looks like derivative. But the A average is delta v over delta t. So by the language of calculus, this is dv dt. So acceleration is dv dt, is a derivative of speed with respect to time t. Okay? And because v itself is equal to dr dt. Okay? So A equal to second derivative of x with respect to time t. Okay. A equal to dv dt equal to second derivative of x with respect to time t. In words, the acceleration of a particle at any instant is the rate at which its velocity is changing at that instant. The acceleration of a particle at any instant is the second derivative of its position x with respect to time t. The acceleration at any point is the slope of the curve of v at that point. This is a vt curve, okay? At equal to dv dt. And we move this k, dv equal to at dt. And we do the integration, so we can do the reverse process. We know A, we find a v. Okay? And this constant depends on this initial condition. Okay? The constant is decided by the initial condition. Now, sample. The figure is an xt. This is xt. This is time t. This is x. For an elevator cap that is initially stationary. This is initially stationary. Then moves upward, which we take to be the positive direction of x. And it goes upward, 1, 2, 3, 4 meters higher, okay, upwards. And then stop at this one, okay, stop at 25, more than 25 meters high. Okay. The velocity of the elevator at any instant is the slope of its position time curve at the point representing that instant. So v is equal to tangent theta, as we have learned before. For example, at 5 seconds more, you do a tangent for this curve, and you get tangent theta. That's the slope, instantaneous velocity at this instant. Okay, and we look at this one. In this area, it's straight line. That means what? That means the tangent are the same. But this means the velocity are the same. So from time 3 seconds to time 8 seconds, the elevator goes up with uniform speed. Okay. We take this theta, a tangent theta is velocity. Okay. Now, let's plot another. We take every point, take the tangent. We find tangent theta. We put a v. This is a v, this time t. We look at this v. In this area, the tangent and theta are the same. So v is constant. V is constant. Okay. In this area, okay, we see the v increase linearly, this area. And in this area, the v decrease linearly until it stops. From stop, we start from A, goes up. So this is velocity. Okay. The red v curve for the cap is plotted from the derivative of the blue curve. Okay. Now, let's do it again. In this plot, v over t, we take the tangent. tangent. In this area, the tangent is 0, right? So this area, the acceleration is 0, because acceleration is a tangent of velocity, right? And in this area, the slope are the same. So this constant for acceleration. And this area is 0. And this area is linear. So this is negative number, because tangent theta is negative number. So this one, okay, brown one, will be acceleration and the t, okay? The brown acceleration curve for the cap is plotted from the derivative of the red v curve. Is a equal to dv dt. At any point, we find that tangent dv dt, tangent is theta, and we plot this one. Sample. A particle's position is given by x equal to 4 minus 27t plus t cubic, with x in meters and t in seconds. A. Find the particle's velocity function v and acceleration function a. They are the function time t. That's simple. We do the derivative of position with respect to time t. Okay, this is 0, this is minus 7, this is a 3t squared. That's it. Okay. And acceleration is do derivative again. Okay, so this is 0, 0, this is 6t. 6t. Okay, we got a v and a. This is given, and we calculate. Question B. Is there ever time when v equal to 0? We say we don't know. We can try. We set equal to 0. Okay. See whether we can find the t. If we can find the t, then we say yes. If we could not find the t, that's what we say no. So let's do this one, v, let's set it into 0. Can we find the t? Yes, we do find the t. T to 3 seconds. Okay. So then we see yes, there is ever a time when a t equal to 0, that is at t equal to 3 seconds. Question C. Describe the particle's motion for t larger than 0. So when we describe the motion, we describe 3 things: position, velocity, and acceleration. Now, that's t0. We know we put t0, we get x equal to 4. Then we see velocity, t0, velocity is minus 7. So acceleration is 0. So when t equal to 0, x is 45 in this direction. And the velocity is minus 7, go to negative direction. Okay, velocity is to negative direction. A is 0. Then we see 3 seconds. This is v equal to 0. That means the velocity will change direction. So let's see what's happening at t equal to 3 seconds. T equal to 3 seconds, we put 3 here, x equal to minus 55. It goes this one is triggered, this is here, minus 50. And the velocity is 0. This one is stop. It goes slower, 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 stop, and return back, right? Yeah. And the acceleration at 3 seconds is positive. Acceleration is always positive, okay? So acceleration goes this way direction. All right, let's see between them. Between them, the speed is getting slower, slow, negative, okay? And the location is in between 4 and minus 40, okay? Okay. Velocity is always negative. Velocity is always negative. Getting smaller and smaller, okay? And acceleration is positive, getting larger and larger, right? So go here, A is larger and larger, positive. V is smaller and smaller until stop. After 3 seconds, everything turns round, okay? everything turned wrong because velocity goes this direction, a goes direction, and getting larger and larger, right? This is the motion. Constant acceleration. Constant acceleration is a special case. It has three formulas you are quite familiar in high school. First is v equal to v0 plus at. The velocity at time t equal to velocity at time 0, initial velocity, plus the constant acceleration times t. Second equation is the distance traveled, x minus x0, okay? This is equal to v0t plus half a t squared. This formula you should be familiar with. And we have a final v squared minus v0 squared equal to as, and s equal to x minus z. Okay? These three equations we are going to use again and again. You should remember that. You have five quantities: v, ling, a, t, and s. Okay, we have three equations. So in order we can find the answer, at least we have to know two. Okay, out of these five, you have to know. Now, special case. Okay, a is constant. Okay, a can be larger than 0 or smaller than 0. dv. Move this one, a dt. We do the integration. And we find v, this is integration, differentiation, cancel out. V equal to integration a dt. And in this special case, a is a constant. So it said, let me out. Okay, I'm constant. And then integration, decretion is t. So get at, okay, vt. V equal to at plus constant. This constant, okay, is the initial condition. Okay. When t equal to 0, v equal to v0. This is called the initial velocity. When t equal to 0, v equal to v0. So we find, okay, c1 equal to v0, and we put it inside. Okay, we got at plus v, and we rearrange them for the v0 plus at. We're familiar with that one. Okay. Or we can do a different way, which is a dv equal to a dt. We do the integration. T equal to t0, this is v0. T equal to t, v is v. And we do this one. This one is v minus v0. This one is at plus c. At, no c, sorry, is this definite integration. Okay. So this is actually this one. We learned that velocity vt is dx dt, the derivative of its position with respect to time t. Now we do this one, then dx equal to v dt. And we do the integration. Okay, this is x, right? Integration, differentiation, x. This vt, we do that. Vt equal to v0 plus at. And we do the integration. This is a v0t. This is half at squared plus constant. It's very simple integration. Okay, and c2 is from initial condition. When time equal to 0, the position is x0. Okay, initial position. So we put it inside. We get x0 equal to v0t half a 0 squared plus c2. We get c2 equal to x0. And we put it inside. Okay, we get s equal to x minus x0, the displacement, equal to v0t plus half alpha t squared, which you are quite familiar with. Or we can do it a different way. We just do the integration. Okay, dx equal to v dt equal to v d t. We do the integration. Okay, a definite inflation. Okay, t equal to 0, v, x equal to x0. T equal to anytime t, x equal to anytime t, x. This integration is x minus x0. This equation equal to v0t plus half t squared. This is exactly at this one. Okay, at this one. Look at the curve. This is acceleration to t. A is constant, a special case, constant acceleration. So this is a line. And we move this v equal to v0 plus at. This is a vt. This is a t. So this is linear. Okay. T equal to 0. This is v0. There's a tangent. This tangent. Okay. So, okay. A. And finally, the x. Okay. This is x0. This is x a function of t squared. So there's a parabola. Parabola. This is the curve. Okay.
A ball rolling down a long incline will be used to show how position, velocity, and acceleration of the ball change as it moves down the incline. 5 lights arranged along the length of the track flash simultaneously once per second. As the ball rolls down, it is directly above each of the lights just as they flash. This gives us a record of the positions of the ball at 1-second intervals. This is how far the ball traveled in the first second. This is how far the ball traveled in the first 2 seconds, 3 seconds, 4 seconds. We will move this distance up to a graph to keep track of position versus time. Does position change linearly over time? Next, we will graph the average velocity of the ball during 5 different intervals to see how velocity varies as the ball rolls down the incline. The ball moved this far during the first second. It moved this far during the next second, this far during the third second, the fourth second. This gives us a graph of the velocity of the ball over time. Does velocity increase linearly? Now we will graph the changes in velocity versus time by graphing the differences in successive velocities. What does this tell us about the acceleration of the ball? The acceleration is constant. We will use a nearly frictionless air track with the glider floating on an air cushion to demonstrate accelerated motion. When the track is level, a push is required to move the glider. It then moves at a constant velocity as shown by these dots that track the position of the glider at half-second intervals. When we tilt the track by placing a 1 centimeter high shim under one end, the glider moves down the track. What can we say about the magnitude of the velocity in this case? The glider's velocity increases with time. It accelerates. If we increase the tilt of the track by doubling the height of the shim, the acceleration increases. When the shim height is increased to 3 centimeters, the acceleration increases again. This split-screen view shows the glider accelerating at all 3 angles of tilt.
V squared equal to V0 plus AT squared. We get this one is V0 squared plus 2V0AT plus A squared T squared. Okay, and look at this one. Okay, we take the 2A out. It's a V0T plus half AT. What is this one? This is displacement x minus x0. this formula, okay, so we write this v squared minus v0 squared equal to 2as, s equal to x minus a. This is the third formula for constant acceleration. You have to remember. Another look at constant acceleration. S equal to x minus x0 displacement, v0t plus half at. We rewrite it in two terms. One is v0t, another is half at. We can look at it, okay, as two movements. One is v0t plus half 0 at. One is 0t plus half at. What does it mean? This is the movement with acceleration 0, uniform speed v0. This is initial speed equal to 0 and constant acceleration. So this is a uniform movement with the initial velocity v0. And this is the constant acceleration with v0 equal to 0. So a constant acceleration movement can be looked at as a composite of two. The direction of the acceleration of a point depends not only the change of its velocity, but also on how the reference axis is chosen. Okay? For example, this is acceleration actually. If we take the reference frame in this direction to right, and then this a is larger than 0, same acceleration. If we take the reference frame x positive to the left, in this case a is smaller than 0. Whatever, they are the same movement. Okay, depends on how I choose the direction of frame. Both are right. Both are right. The magnitude of the acceleration of a point depends on the changes rate of its velocity. It has nothing to do with magnitude of the velocity itself. Look at this one. We have familiar this vibration, okay? And you look at this one. At this neutral point, it goes back velocity to the last. X is very small, velocity large. And at the two extreme points, okay, velocity is 0, but acceleration is very large. So position, velocity, and acceleration are independent with each other. Their dimensions are different. So big velocity does not mean big acceleration. Acceleration is the change rate of velocity. Look at this is the velocity. At x smaller, velocity can be larger. X larger, velocity can be smaller. That's different things. Free fall acceleration is A is constant equal to G is approximately 9.8 meters per second per second. It's a free fall acceleration. G we call gravitational acceleration. Free fall means that falling without resistance, falling in vacuum. The acceleration G is independent of the object's characteristics, such as mass, density, or shape. The value of G varies slightly with latitude and also with elevation. The sign of G depends on how you choose the direction of the reference axis. It is a constant acceleration, so we can use a set of formula for constant acceleration. Replace A with G. So this is when A will replace with G. Okay, that G is direction always downward toward the center of Earth. If we take the reference frame X, a Y direction upward, then in this case, G is negative number. So this set of formula become, replace A with minus G. V equal to 0 minus GT. Y minus Y0 equal to V0t minus half GT squared. And V squared minus V0 squared equal to minus 2GS. Okay, 2GS. And if you don't like this choice, you want to choose the Y direction downward. And then in this choice, G is positive number. And we replace A with G. We get another set with positive number. Okay. So these two set formula, which one is right? This depends. In this case, this is right. In this case, it is right. If you use this reference and you use this set, you're wrong. Okay? You're wrong. Both are right. Both are right. Free fall is a movement with a constant acceleration g. One of its features is that its velocity is 0 at top. Remember, the velocity is 0 at the top. With that information, once height h is given, we can easily find the time when it reached the ground, because h you could have gt squared. Okay? You have h, you can find the t. Or the final velocity, because you have h, this is the final velocity, and vice versa. Remember, velocity is 0 at the top. The time from the top to the ground for a free fall subject equals the time for the subject to be soared up from the ground to the same height. Up and down, they take the same time. The falling speed at the ground for a free fall subject equals that of the subject being soared up to the same height h at the bottom. The velocity at the same point, whether it's up or down, they are the same value. Okay? This is a feature of free fall acceleration. Sample. A pitcher tosses a baseball up along a y-axis. This is we take y-axis going up with an initial speed 12 meters per second. Okay. Question A. How long does the ball take to reach its maximum height? Whatever, we write down three formulas. Here we use minus g because we take y direction is up, g is down. Okay. And we see which one we can use. In this one we see, what do we know? We know initial speed, v0. Okay. And we know what at top, okay, v is 0. So this no, so we can find the t. We take this formula, easy one. Okay? So t equal to v minus v0 over minus g. We get 1.2 seconds. Question B. What is the ball's maximum height above its released point? What is maximum height? We still use the condition at the highest v is 0. Okay? So we take these three formula out and we choose one. This is the one we use. Okay? V squared minus v0 squared equal to 2 delta yg. Okay? We know this 0, this 12, this natural, we get a y, 7.3 meters. Okay. Question C. How long does the ball take to reach a point 5.0 above its release point? The maximum is 3.3. I want to find the value. Time you get to 5 meters above your position. That's very easy. Okay. We know delta y. Delta y is 5.0. And we know this one, you can find a t. Okay. So we get a 2t. This is 0.53 second and 1.96. We choose which one is right. The answer is Both one are right. Why? Now, when you toast this up, a time t equal to 3.53 seconds, this one, 5 meters per, is going up. Okay. And then it's going up and return. I get this same position. Okay. 5 meters high. This is 1.9 going down. And up and down, the speed are the same. We didn't calculate. Well, I can tell you that one. Okay. So these two, both are right.
When a meter stick is dropped, the distance it has fallen increases with time. We'll use that fact to measure the time it takes a person to react after a meter stick is dropped. One person holds a meter stick vertically, while a second person waits with her fingers poised at the 50-centimeter mark on the stick. The stick will be dropped unexpectedly, and the second person will try to catch it as quickly as possible. The distance the stick falls before it is caught will show how quickly the second person reacted after the meter stick was released. This is how far the meter stick fell before it was caught. What is this person's reaction time?
Next lecture, Chapter 2, Motion in 2 dimensions and 3 dimensions. Welcome you make a comment and give suggestions so that this program can be more helpful. Acknowledgement. This video clip is a part of my lectures on college physics during 1990 to 2021, based on the adapted textbook, Principles of Physics by Holliday, Resnick, and Walker, published by Wiley. The demo videos were bought from a company in USA by my university for teaching. They helped a lot. I'm sorry for not remembering its name to show my appreciation. It seems that they came from the University of California, Santa Barbara, where I got my PhD in physics. Thanks God.